Okay, this is your Unit 5, Lesson 3 homework. This is day 1. This comes from OIO page 380 in the Course 3 of the Core Plus Mathematics series, Book 3. And so we're taking a look at question number 1, which deals with the cannery designs. And so you're dealing with the volume of a can and the surface area of a can. They give you two very nice equations for that. And part A of this question asks us to write the volume, or the rational function h of r that gives the height h of the can as a function of the radius r of the can. Background information, this is a can of corn that holds 500 centimeters cubed of corn. So what we have is a can that we know holds 500 centimeters cubed, so that's the volume, and volume is going to equal pi r squared, h. So we're going to solve this for h. So we'll do that by dividing out the pi, the r, and the pi r squared. So we'll divide pi r squared out all in one big motion here, which leaves us that 500 over pi r squared is equivalent to h of r. So that is our first equation for the volume. Then part B, we're asked to take a look at, based on your results from part A, write a function s of r to calculate the surface area of the can for any given radius r. Well, our surface area equation is given to us by 2 pi r squared plus 2 pi r h. Well, if we analyze it a little bit, the 2 pi r squared is twice the area of a circle. Pi r squared is the area of a circle, top and bottom of the cans. And then this 2 pi r h is the circumference of a circle. That gives us the length of the rectangle times the height of that rectangle. Now this h is the part that we're going to substitute from part A. So our surface area will be equal to 2 pi r squared plus 2 pi r, and then substitute in the 500 divided by pi r squared from part A for h. We'll simplify this a little bit. This is equivalent to 2 pi r squared plus 2 pi r times 500 all over pi r squared. And I lined up the pi's and the r's together so we can see that the pi's would cancel out, and we lose one r on top, which eliminates r, and then one r from the bottom, which leaves just r. So this simplifies to 2 pi r squared plus 2 times 500 is 1,000 all over r. So this is our s of r equation in simplified terms. Now part C asks about a practical domain for this function. Now the only thing we have to be worried about really is that we can't have negative radii, so we want to make sure that we're above 0. I can't divide by 0, so this r value here can't be 0. But then I'm really allowed to let the radius be whatever I want it to be. But if you stop and think about this can of corn, you know, most of the cans of corn you see in the supermarket have a given value that is well less than even 20 centimeters. So for the time being, we're probably going to consider only a practical domain between 0 centimeters and 20 centimeters, where 0 is not included. So let's go 0 to 20. I'll write that down like so. Then we're asked to sketch a graph of this function. So I'm going to do that. I'm going to do that using my Inspire. So I'm going to pull that out here, turn that on. And so I have the graph function rule already up here. Let's bring the rule up. So we go 2 pi r squared, that's x squared, since we're using x's here, plus, and if I want to put the back end as a fraction, I can go to the script key, which is the box key, and let that be a fraction by typing in 1,000 divided by x. Now I mentioned that my window, I'm going to hit enter, but I want to change the window to match this. And you already see some negative things happening over here. But let's go ahead to the window settings, and we're going to let this go from 0 out to 20. And then let's my y minimum be 0, but then let's let this x maximum go pretty big. We're given 500 centimeters cubed for the volume. Maybe 500 is where we're going to start and see if we need to zoom in or zoom out based on that. So there's my 500. And sure enough, I'm starting to see the curve up here. Okay? And so this curve kind of looks like a parabola, but you'll notice that it's not symmetric like a parabola. It has a little skew to it. Now, if I kept zooming out, you'd see even that this value up here gets closer and closer to 0, where the vertical asymptote would be. And then this appears to be some sort of maybe oblique asymptote. But from this graph, we're able to see at least some information about, hey, there's this minimum surface area idea. And so that minimum surface area idea is going to come into play in the next question, so that's going to be an important feature. So let's go ahead and give a little sketch to that on the side. I'm going to let that sketch go here, kind of like so, and then indicate what I used for a window. I went 0 to 20 on R, and I went 0 to 500 on the S of R's. Okay, now part D. Part D wants us to determine the minimum value on this practical domain and then give the radius and the height. So I want to find that value. So I'm going to go back to my graphing calculator, and I'm going to go to the menu, and I'm going to analyze the graph and look for the minimum value. And I'm going to give it a lower bound, upper bound, and it appears like we're dealing with a minimum at 4.3. That's 4.3 for a radius, and the surface area looks to be about 349 centimeters squared for a surface area. But if R is 4.3, we need to find H. And so H is given to us by plugging in the R value of 4.3 into the original part in part A. So we're going to do that. We're going to type this in and do 500 divided by, I'm going to use a set of parentheses here, pi times 4.3 squared. I'm going to enter on that, and I get a value for a height that's about 8.6. We use 2 digits, 8.61 centimeters. So we're dealing with a can that's 4.3 centimeters in radius, 8.61 centimeters in height. And that really ends the part 1 of day 1's homework for Unit 5, Lesson 3.